So that first search we said the previous logic is going to be errors because keep iterating infinitely when we not keep tracking on the visited vertices. So that's why we want to keep tracking this by have the condition to check if vertex is not marked. Then we're going to mark it and keep pushing it into adjacent vertices on the stack. Now, when we visit Atlanta, since we already visit Houston, we no longer push Houston back into stack. We're going to put Washington. And then we go back, right, to say vertex equals stack.top. Now it's Washington out. And stack.pop, pop Washington out. If vertex equal to n vertex, yes, because now we top, which is Washington equals to Washington, then we set file to true. We never longer do else, and we never do the loop anymore because we do it when it's not found. We return found, then its path is found. Now this correct algorithms, but in order to implement this, we have to create a collection of the path. So to implement this, we use Q as the vertex Q. So this is going to collect the path that we visit, which is start from Austin, Houston, Atlanta, and Washington. Then we get a path from beginning to the start to the end of the destination. So we pass the graph in, create a vertex Q to keep track the path, and stack. This is just to use for that first, right, to see if it's have any adjacencies, and visit them all and pop them all out after you visit and mark them. So first we clear out the marks, keep pushing, push the start vertex that we already explained the algorithm earlier, and then look at the top and then pop it out. If vertex equals to n vertex, then return true. Else we just going to say if graph is marked. So if graph is not marked, so we want to look at if all the vertex are marked, if all the vertex are visited, and we're still not finding it, then we're going to keep popping out until there is empty, and then we return file to false. Otherwise, we're going to go and check, like the first level, check if all the vertices is marked. The second level, we go in and say, actually the first level here, just check that vertex is marked. That vertex is marked is the top that we pop out. Like in this case, it's Austin. Austin never marked. Then we go in and mark that Austin is visited. And get the graph to vertices. Like this is just get two vertices, pass Austin in, get two vertices, return, or the adjacencies to Austin to vertex Q. Now while vertex Q is not empty, that means that adjacents to iterate through. So vertex Q.dq, so you dq it out to the item and make sure that is it marked. If it's not marked, then push to the stack. And we keep doing this again. Alright, so let's look at this in details again. So we said Austin is not marked, mark Austin. Now get two vertices of Austin. So get two vertices of Austin, we should get all the adjacency vertices, which is Dallas and Houston. So Dallas and Houston returns into vertex Q. Now vertex Q is not empty while we're going to loop into that vertices. Item equals to vertex.dq. So vertex.dq, since we have Dallas and Houston, we do NQ Dallas, we do NQ Houston. Then if it's a Q Dallas, we NQ Dallas first. Dallas is going to go DQ first. So Dallas is an item. So we said if we want to see if dollar is marked. If it's not marked, then we can push dollars into the stack. So dollars is now in the stack. So go back to the top. So we look at vertex is now dollars. We pop dollars out. So vertex equals to end vertex. No, dollars is not equal to Washington. We do else again. Right, so if graph is marked vertex, so we want to check if we already marked dollars. No, we didn't. So we will mark it as we visited. So now get two vertices of dollars. So go back, get two vertices of dollars, right? We can get Denver. So Denver and Austin, right? So we have two, Denver and Austin. So now Denver and Austin is going to be on the vertex Q. So Denver and Austin. Now we go to look at vertex Q is empty. It's not empty. Then we're going to DQ. So if we have Austin first, if I say NQ Austin Denver, right, alphabetical order. So Austin come out, but it's marked. Then we're not going to push anything. So we go back. Right, it's isolating back. Is it empty? It's not empty. When we DQ back, now we get Denver out. So Denver is not marked, then we push Denver in. So Denver in is not marked. We're done with all the iteration here. Go back into top Denver and pop Denver out because we push Denver stack pop out. So if vertex equals right, vertex is Denver is not equal to Washington end vertex. So false go to false. We did the else again. Now, if Denver is marked, no, we marked it as visited. So now visit Denver, get adjacency to Denver, and now go back. Adjacency to Denver is what? Atlanta, Chicago, and Dallas. Right. So we keep doing this again until we get. Let's say we get to Atlanta, and then Atlanta is going to get adjacency again to Washington, and we found an exit. So loop is keep doing that in the same process I show you. So now this is called let's first search approach. Right, we look at depth first already, right? This is depth first search approach. Now let's look at breadth first search. Let's say for breadth first, you're going to go to Austin to Dallas, and then Austin, Houston, and then Dallas to Chicago, and Dallas to Denver. Right, and then go back Houston to Atlanta, then go back to Chicago to Denver, and Denver go to Atlanta, Atlanta to Washington. It's going to spreading out. So the algorithm should be very similar, but making sure it's spreading out instead of going depth. So let's look at the algorithms now. Start vertex, end vertex. Same file return true. First we clear the marks. Q, we use Q instead of stack. Right? We do NQ, the start vertex. So Q, we start to DQ, the vertex. So for example, Austin, we NQ Austin, we DQ Austin. If vertex equal ends vertex, no, else vertex is not marked. Mark vertex as visited, Austin visited, NQ all adjacent vertices onto the Q. So when you start to NQ all adjacents, then we will get all adjacent Austins is Dallas and Houston. So we have Dallas and Houston into the queue. Dallas and Houston into the queue. So if queue is not empty, then we go back and we do DQ. So when we do DQ, we NQ dollars, then we DQ dollars out. Dollar is not visited, so it's not equal to n vertex, and it's not visited, then mark as visited. And NQ urgency of dollars again, so we see that our urgency of dollars is going to be Chicago, Denver. So same, we start to DQ. Since it's NQ and DQ, that's why it's not going to depth. Because when we DQ back, we DQ Houston, it's go back to Houston, and then start to NQ Atlanta. And then we DQ back again. We DQ back, we DQ Dallas. No, we DQ Chicago, and then we NQ Denver. Let's just keep doing that based on sequence. That's why let's go to breadth first. But stack, always look at the top. So last in, first out. So that's what always go to depth, depth, depth. So that's a technique. Q, just do breadth first. And the same other logic is the same. Just change stack to the Q. Because Q first in, first out. When it's first out, then that's why I have to go to the urgency of that first visit cities. And this is just implementation, pretty much the same. Just change from stack to Q. Right, and the rest is the same. Check mark or not. Alright, so we understand the best first and depth first search. And that's how we do travels. So after we have all the possible path, there's a path to travel between cities, then we can make a single source shortest path algorithms. Now we can find a shortest path from the start to the end destination, right? So an algorithm that displays the shortest path from a descendant city, starting city, to every other city in the graph. So in our example here, we say starting point is Washington. I want to see two other cities. So Washington to itself is 0 distance. So it seems like these wedges are the distance then. So Washington to Atlanta is 600. Washington to Dallas is 1,300. And now I start to look at form Atlanta itself to Houston, or the adjacency, right? Dallas to Austin, Denver, Dallas to Chicago. So these are all the distances. So we start to create a shortest path. So we said algorithm for the shortest path traversal is similar to those we use for the depth first and best first searches. But there are three major differences. We can use a priority queue rather than a first in first out queue. We stop only when there are no more cities to process. There's no destination. It is incorrect if we use a reference-based priority queue improperly. For the shortest path traversal, it's very similar to depth first and breadth first searches, but they don't use queue. Queue is first in first out, right? They use priority queue instead. I mean, queue is first in first out, yeah. And they don't use stack. Stack is first in last out. That's the depth first algorithm. And first in first out is the breadth first algorithms. But we want to the shortest path. That means we're going to use a priority queue. So this is where priority queue is going to come in. We stop only when there are no more cities to process. It is incorrect if we use a reference-based priority queue improperly. So we can look at